Hello, everyone. Welcome to our live session for, what is this, 420, so on March 20th, 2021. Welcome to our live astronomy session. My name is Matthew, and I am one of the course staff for the online courses that we run on Coursera and Udemy. I'm going to hand this over to Professor Impey, who will welcome you, and then we'll get started with your live questions.
Okay, good to have you all here on April 20, not March 20, but that's our regular live session for the online classes. And having done a special session on space travel, the floor is today open for any topic in astronomy.
And thank you for that correction. My apology. That's right. It is April 20th. The very first question that we have for today is from one of our live participants, Parth Sarda. I'm sorry, the first one is from Cheeky Bear, who would like to know, could a traveling rogue planet have a ring system, or would the speed of the planet rip the rings away?
So let's start with what a rogue planet is. Rogue planet is the term for a planet that doesn't orbit a star. The reason such planets exist, and it's fairly tentative because I think there are only a couple of candidates been observed so far, is that in the early formative stages of a solar system, the interactions and dynamics are very extreme and unstable. And simulations suggest that in many planetary systems, maybe even the majority, one or more early forming planets are ejected from the system due to gravitational instabilities and interactions and collisions even. And so the prediction out of our theories of how planets form is that there are going to be a substantial number of planets, some estimates even say as many as the number of planets in normal star systems, but I think that's an overestimate, that are free floating in space without a star to illuminate them. That means they're extremely difficult to detect, of course. Now, given the vacuum of space, if such a planet had a ring system, or if it had orbiting moons and they were held by gravity, the ring system or the moons, then they would not be disturbed by the ejection of that planet from the system, unless they were destroyed, unless a ring system or a moon were destroyed in the actual interaction that led to it being ejected. Equally, a rogue planet can carry its own atmosphere, just held by its mass, and so if these are super-Earth type planets, they could actually carry quite thick shielding atmospheres, and then also a massive planet like a super-Earth would have a lot of geological heating. So it's conceivable that these could be habitable worlds, some of them.
Excellent. Thank you very much. The next question is from Parth Sarda, who would like to know, what do you say, or what are your thoughts on the existence of intermediate mass black holes? And perhaps you can just talk about the spectrum of black holes and black hole sizes.
Right. So black holes, nature appears to be able to make black holes of essentially any size, ranging from a dead star mass black hole, the minimum of which is about 3.5 times the mass of the sun. So that's the fate of essentially a star that starts its life as about 10 to 15 times the sun's mass, loses mass along the way, including in a supernova explosion, and the collapsed core is 3.5 times the mass of the sun. At the far other extreme, we have the most massive black holes in the center of active galaxies. And the estimates are a little uncertain, but there are several that are claimed to be 10 to 20 billion times the mass of the sun. And the black holes in galaxies range all the way down to a few million times the mass of the sun, with the Milky Way being a prime example. The intermediate mass spectrum ranges from black holes that are too big to be left behind when a massive star dies, so that would be bigger than maybe 30 or 40 or perhaps 50 times the mass of the sun, but smaller than would be expected in any galaxy, which is roughly 1 million times the mass of the sun. So you have a couple of orders of magnitude there, the range of tens of thousands of times the mass of the sun to a few 100,000 times the mass of the sun. Those are intermediate black holes, and they're rare. Very few have been found, but some have been found. And the most common location for these is globular clusters. So globular cluster is a collection of millions of stars, and the density in the center is high, and so these dense stellar systems can actually have enough gas congregating at the center that compression will form a black hole, and these are intermediate mass black holes.
Excellent. Thank you very much. The next question is from one of our live participants, Dimitris Siropoulos. Would like to know, do you believe that the deployment of the James Webb Space Telescope will be the next big thing in astronomy and will establish new theories, or do you think it will mostly just affirm or check on old ideas?
It's a good question. By its anticipation that awaits its launch as the successor to Hubble Space Telescope and the enormous price tag associated with it, over $10 billion so far, it is certainly the next big thing in astronomy. It's a 6.5 meter telescope, by far the biggest telescope we will ever have had in space, and it's also by far the most expensive facility at the time it's launched. So it's the biggest thing in astronomy for sure. As to what kind of discoveries it will make, it's actually, of course, classically hard to predict what discoveries will be made by a facility. Now, it's not doing exploratory science for the most part. Time is hard enough to get on these telescopes that you can't really apply on time for time on a telescope like the James Webb and just say you're going on a fishing expedition. So essentially you have to write fairly focused proposals to follow up phenomena or observe things in detail or answer a scientific question. And that in practice actually limits the possibilities of the telescope to make truly surprising discoveries. So there's a little tension there between wanting to do productive science, recognizing that in a highly competitive situation you can't just give people time on a speculative hunch, and yet in science it does pay to be open-minded and to be able to make observations that lead to chance discoveries. For telescopes like the James Webb, the complicating factor is that the field of view is very small. You can only look at very small patches of sky. So the odds of it picking up something randomly while observing something else are quite small. That is in contrast to some of the survey telescopes that we're talking about. So a counterpoint, I would say, would be the Vera Rubin Observatory, formerly called the Large Synoptic Survey Telescope. Because that telescope is going to observe the whole southern sky to Hubble depth every 3 days, it's very likely to find surprising things.
Excellent. The next question is from one of our live participants. Can dark energy be thought of as anti-gravity, and how does it react with gravity?
In a sense, it does act like negative gravity. I mean, there's no such thing as negative gravity as a concept, because gravity emerges out of a theory of general relativity, and that theory does not accommodate a minus sign in front of the force so that it has the property of anti-gravity, if you like. The physics way to think about it is in terms of the equation of state. So any medium, any fluid, any substance has what's called an equation of state, which relates the pressure and the density and the volume, sort of like an ideal gas has an equation of state. And dark energy has an equation of state with a negative sign in the equation, and that indicates that it exerts negative pressure, and that's why in the theory or in the physical description space-time is expanding because of dark energy. But it's not related to gravity in any formal sense as far as we know.
So that kind of answers the next question. Does it tell us anything about the unique nature of gravity, or do we think they're totally separate?
In terms of with the relationship of dark energy to gravity, at the moment we think they're separate. We have a pretty robust theory of gravity, general relativity. We have no viable theory for dark energy. And people trying to sweep dark energy into the picture by extending or altering the law of gravity, general relativity, have not had any success so far. So at the moment we don't think they're related.
Isla Holroyd would like to know if or when will the cosmic microwave background signal end?
In principle, it will never end. As space expands, the microwaves that flow through space, through empty space, are stretched by the expansion. That's the redshift. And that expansion continues and the wavelength keeps stretching. And I suppose at some point in the far future, if the universe keeps accelerating in its expansion, the microwaves get stretched infinitely, and at that point, logically, they have zero energy. And at that point, essentially, they disappear. But until that point, and infinite time is, of course, hard to grasp, all that's happening is the wavelength is getting longer and the energy is getting lower. So that's just a very steady process. Now, something interesting does happen at some point in the far future. What happens in the far future of an accelerating, expanding universe is that at some point the horizon, that is the limit you can see from your region of space-time, given expanding space-time, becomes larger, or rather the wavelength of the microwave stretch become larger than your horizon. And at that point you can't even see the microwaves from the Big Bang. So even though they don't disappear entirely or go to zero energy, they eventually become unobservable.
Carrie Lee asks, is everything in the sky essentially the past we are observing? And if so, why can we see the past but we can't see into the future?
Yes, everything in the sky you see is the past. That ranges from very recent past, the moon, which is seen as it was just about a second or so ago, to the sun, which we see as it was 8 minutes ago, to the brightest stars in the sky, or the nearest stars in the sky, which we see decades ago, to the most distant stars you can see with the naked eye, which actually are thousands of light years. So we see them as they were millennia ago. So everything we see is in the past due to the finite speed of light. If light were infinite speed, we'd see everything as it is now, simultaneously. But there's no way within conventional physics to see into the future, because that would violate causality. And causality, the fact that actions have causes that we can identify, is a foundational principle of all science.
World of Science, who's on with us live, would like to know, what role would nuclear propulsion play in the future of astronomy or space exploration?
Well, nuclear propulsion should play a big role in the future of space travel and space propulsion, but it's going to need some research that's happening rather slowly. All the private space enterprises, everything NASA does, everything the Russians and the Chinese do in space is done with chemical rockets. It's really a technology that hasn't changed for 60 or 70 years. Nuclear propulsion, in principle, could be much more efficient, thousands or hundreds of thousands of times more efficient. But the technology to put a nuclear reactor, first of all, to miniaturize it, and second of all, to put it into orbit or in space and have it work reliably, has not yet been developed. And in fact, even the preparatory research has not been done. So we are actually very far from demonstrating or prototyping nuclear propulsion in space. By very far, I mean decades and possibly 50 or more years.
Art Studio would like to know if you can talk about vacuum decay. How is it caused, and what impact does this have on us?
So vacuum decay is the idea that the vacuum of space has an energy, and that the vacuum states defined in terms of vacuum energy can actually decay, which typically means they're transitory states, evanescent states, if you like. Now, this is a theoretical idea. We don't actually observe vacuum decay directly. We observe vacuum energy. We can measure that in the lab, and we can show that the vacuum of space does have a tiny amount of quantum energy associated with it. But vacuum decay is not directly observed. It's something that's just inferred.
All right, the next question is from Thomas Coverdale, who says, I have been troubled by the idea of inflation. It seems like an unsupported fudge factor to make the theory fit. Could our accelerating expansion be a continuing influence of whatever inflation was?
Inflation can seem a little ad hoc. The rationale for inflation was originally to explain two things that are not predicted simply out of the Big Bang model. One is the flatness of the universe, the fact that it's spatially very close to flat or Euclidean in 3 dimensions. And the second, that the universe is very smooth and homogeneous, that it doesn't have any variations in density or the amount of material at any place we look. Those are not naturally explained in the Big Bang model. Inflation expands them by positing a very early, fraction of a second, exponential expansion of space-time to the point where the space-time gets flattened and then continues its more sedate Hubble expansion. That stretching also takes out inhomogeneities or lumps or monopoles or other artifacts left over from the early dense phase, and so naturally ensures that the universe will both be smooth and flat. So inflation was invented to explain those two features, and can, of course, therefore get credit in the fact that it does explain them. The question then becomes, does inflation have other observable consequences that we can look at to confirm that it's a good idea? And it has tentative support in terms of the power spectrum of fluctuations, that is the amount of fluctuation power that would lead to structures on very different scales, showing a logarithmic form. That's inflation would predict that, and that's what we see. And then there's some more subtle theoretical things that inflation does seem to check the box on and match observations. But it's not by any means a completely confirmed theory. Also, inflation is not really one theory, because when we don't know what the so-called inflaton field is, that is the quantum field that led to the expansion early on, this exponential expansion, then we can't really fundamentally test it because we're not testing a very concrete theory. There are a number of ideas of what the inflaton field would be. Now, none of those correspond to the entity that we think is causing the acceleration and expansion of the universe. So, although it seems inevitable to want to make an analogy, the exponential expansion in the first fraction of a second and the exponential expansion that kicked in about 4 or 5 billion years ago seem to be physically distinct.
The next question is from 800 millimeter telescope project. Is there a reason why dark matter should be diffuse and homogeneous? Could it agglomerate in larger stellar-sized objects that would not be visible?
It isn't actually completely smooth and homogeneous. Dark matter does have structure, it does clump, it does obey gravity. So whatever dark matter is, and at the moment we think it's a fundamental subatomic particle, it exerts gravity on itself, on other dark matter particles. And so dark matter over cosmic time will clump. It doesn't clump as dramatically as normal matter, the stuff we're made of, and that's for the simple reason that normal matter, when it collapses, has ways to dissipate energy that accelerate the collapse and lead to the formation of stars and galaxies, the visible parts. Dark matter doesn't have that mechanism because it has no interactions with radiation. And so the clumping or clustering by gravity of dark matter is more subtle, but it does grow over cosmic time. And so as cosmic time has gone by, there are dark matter potential wells or agglomerations of dark matter on all different scales. The size of galaxies typically up to clusters and superclusters. We don't tend to see dark matter objects much smaller, so we don't expect dark matter stars or planet-sized objects, and none have been seen. It's gentle enough in its gravity over time that it really only manages to make concentrations on large scales of galaxy size or bigger.
The next question is from Art Studio Live, who asks, how can we avoid time dilation due to the movement of Earth around the sun?
We can't avoid time dilation. Time dilation is an inevitable effect of relativity, special relativity. And so the motion of the Earth or any object with respect to a reference frame of the sun or something that's not moving on a larger scale is going to cause time dilation. But for the motion of the Earth, which is tens of kilometers per second, a tiny fraction of the velocity of light, the actual amount of dilation is very small. It's measurable, but it's very small.
The next question is from Addie, who asks, how are tardigrades used as astrobiology models?
Tardigrades, first of all, are a very interesting creature. They're called extremophiles, which is to say living entities that can handle extreme physical conditions and chemical conditions. Most extremophiles are microbial, but tardigrades are actually small animals. Their nickname is water bears. I think they were discovered in the 1770s, actually, by a German biologist. And they were seen under the early versions of the microscope. So they're no more than about 1 millimeter in size. They have 8 legs. They have digestive system, a single gonad. There are 900 species in one phylum, so they're not just even one species. And they have this extraordinary ability called cryptobiosis, which means when conditions are tough or when there's not much available water, they will essentially dehydrate. They'll go down to a state where their water content drops to about 1%. That's far lower than any living organism on Earth otherwise. And their metabolic rate drops by 2 orders of magnitude. And they can survive in that state, we know, for at least decades and perhaps for centuries or longer. So tardigrades are kind of extraordinary creatures. Some have traveled accidentally into space. and one experiment was a deliberate experiment, and they even can survive modest amounts of time in the vacuum and incredible cold of deep space. So they're extraordinary creatures. NASA scientists are actually studying them to try and perhaps understand how humans can develop the scale of cryptobiosis to suspend our animation, to maybe allow us to go far distances in the solar system and beyond.
The next question from one of our live participants is, if the G2 muon results hold up, will it lead to an explanation for the missing matter? He says antimatter, but the missing antimatter or matter in the universe.
I think the G2 muon results, if they hold up, and that's a big if, they're in the tentative category. They're at the significance level in scientific terms with 3 sigma, 3 standard deviations, which doesn't happen more than 1 in 1,000 times by chance. That sounds safe, but in high energy physics there have been false alarms in the past. So high energy physicists, because of the difficulty of controlling for everything and the existence of pervasive backgrounds in their experiments, they hold a gold standard that's higher. It's 5 sigma, at which point the chance of it happening randomly and not to a physical effect are 1 part in a million. So this result is not at that gold standard yet. If it holds, however, it does have the promise of new physics, but it does not obviously necessarily relate to dark matter. In fact, it's more relating to the fundamental asymmetry in the forces of nature.
The next question is from Brandon Gaskins, who asks, are there any ideas to detect planetary systems that are oriented perpendicular to our view?
Yes, the best way to detect them is, of course, by imaging, direct imaging, because when a planetary system is perpendicular to your field of view, the planets are at their largest angular extent from the star. It means they spread over the largest angle on the sky, and that maximizes or optimizes your chance of seeing the planet relative to the star. And of course, if you watch it, you'll see it do an entire orbit. And we do have some examples of planetary systems like this. So for imaging, that orientation is favored. For of course all the other major methods of the Doppler, the radial velocity or Doppler method, and the transit method, it's the opposite. You actually want the orientation angle to be edge on, because that's what gives you the maximum Doppler effect, and that's what allows a possibility of this planet transiting the star.
And kind of a follow-up to that is, could we use the light of a separate star that is further away and happens to be behind or move behind the studied star?
The way that can lead to detection of planets is through the microlensing method. So when you have 2 stars in different regions of space where one just happens to pass exactly in front of the other, and this will happen, about 1 in a million stars at some point is going to drift in front of a background star. When that happens, according to relativity, general relativity, you have microlensing, which is to say the intervening star acts as a gravitational lens of the background star. Because the mass of the object is small, the angular deflection of the light caused by the lensing is very small, microarc seconds, which is why it's called microlensing. But the light brightens in a very predictable way that doesn't depend on wavelength. And so microlensing has been used to detect actually several dozen exoplanets, not as many as the other methods, but it's a very important technique. And so that what you're describing is actually microlensing.
All right, the next question is from one of our live participants who would like to know, Ragnar Lodbrok would like to know if you can talk about the difference between a dark matter detector and a neutrino detector.
Yes, they do share some similarities in the sense that dark matter interacts very weakly with matter just by gravity and not at all with radiation. And neutrinos also interact, they're weak force particles, so they also interact not at all with radiation, and their gravity is modest because they're light particles. So there's some analogies between how you detect each of those particles. And in fact, the direct analogy is that often you use a physical collision of the particle, the neutrino or the dark matter particle, with a solid substrate like a solid state detector or a large volume of pure gas atoms or a solid state system, and you look for mechanical or physical resonance or collision with the detector material. And that is a way that both of those types of particles are detected. Of course, a dark matter particle hasn't been detected yet, but that's essentially the method we're using.
Excellent. The next question is from Doctress Newtopia. Why is the COPUS committee, I'm not sure, COPUS committee on the peaceful use of outer space so ineffective in stopping a new space-based arms race?
That committee, that acronym of COPUS, is a legitimate international committee. The trouble is, you might say, the toothlessness, if you like, of the United Nations. So it's very clear from things that are nothing to do with space exploration and weapons in space that the United Nations, has difficulty achieving consensus, because on anything that relates to security, such as weapons in space, the members of the Security Council have to agree. They have to unanimously agree. And since that Security Council includes Russia and China, who have their own superpower ambitions, the odds of them agreeing on things, if it doesn't suit their strategic interests, are low. So COPUS is really sort of hamstrung by the inefficiency of the UN or the lack of any other international organization that can adjudicate issues of space. So the provenance of space, its issues of ownership, issues of weaponization of space are essentially unresolved at this point.
The next question is from Faisal Al-Gamhadi. Why are the giant planets gas and not ice?
Well, some of them are ice, and they do include ice. So as far as we know, the giant planets in our solar system are really two slightly different kinds. Jupiter and Saturn are structurally different from Uranus and Neptune. The large gas giants, Jupiter and Saturn, are believed to have rocky cores. And then those rocky cores attracted mantles, extended envelopes of hydrogen and helium. And at the base of those atmospheres, the hydrogen and helium takes a very strange physical state. The dominant hydrogen actually is compressed into a liquid and then actually a metallic form where electrons and current could flow through it. That's a very strange idea, metallic liquid hydrogen. And that's their basic structure. Now the ice giants further out in the solar system have very unusual structure. They also have rocky cores, as far as we can tell, but because of the distance from the sun, they have a lot of frozen material, frozen volatile materials, such as water ice, of course, carbon dioxide, and methane and ethane ice, and maybe even nitrogen in the frozen form, depending on how far away they are. So Neptune may have that. And so these are frozen ices. And so these ice giants, if you like, Uranus and Neptune, do have a lot of ices in them because they're so far from the sun and because the pressure is sufficient to turn a gas into a solid. And that makes them very interesting objects. We don't really know what that physical state of matter is on the Earth. Very hard to recreate here.
The next question is from a live participant. If intelligent alien civilizations exist, which many believe, wouldn't they be likely to use robots to observe our planet? And if we believe that's possible, how should we change our search for them?
So it's a good point that if you speculate that intelligent aliens exist, that implies that they're our level of development or further. And if they're our level of development or further, then they clearly will have robotic technology, as we already do. And our robots are getting better every year. Decade by decade, they're getting dramatically better. So it's a logical presumption that intelligent aliens need not travel through the solar system or their part of the galaxy themselves, which is a difficult thing for biological organisms to do, as we know. But they would actually send robots. So robots are more durable. Robots can proliferate by building copies of themselves and spread exponentially through space. and they can send their results back, their monitoring, their investigations back at light speed to the home planet. So it's indeed a very sensible premise that intelligent aliens have used robots in the ways that we might think we would use just for travel. They actually use to learn about what's going on in their galaxy.
The next question is from one of our live participants, Tristan, would like to know, is there an explanation on why gravity is so weak, and I assume, compared with the other fundamental forces?
Mm-hmm. I realized there were two parts to that last question, so I'll answer the second part as a separate question, which is if intelligent aliens have created robotic technology, which is a not unreasonable premise, then if they've done it, would we know about it, or how would we know about it? And the answer to that is tricky, because the answer is we may not know about it. Think about what we do with our robots. On the Earth, we use them to do things that humans would do. But we have robotic cars, we have robotic machines of various kinds. Out in space, where energy is at a premium, there's a drive to miniaturization. And so robotic space probes are likely to be very small, miniaturized and propelled perhaps by solar sails or by miniaturized nuclear plants. They could actually be very small and therefore very hard to detect. So even if a hypothetical civilization were surveying their part of the galaxy with robots, they could be so small and unobtrusive that we would simply not know they exist. So now let me redo that last question.
Certainly. The next question is there an explanation for why gravity is so weak?
No. That is a big question, because we have four forces of nature, and they vary in strength from the weakest, gravity, to the strongest, the force that keeps the nucleus of the atom together with gluon exchange particles. These differ from each other by almost 40 orders of magnitude of strength, which is an incredible amount of difference. And there's no theory of nature that we know of that can accommodate this vast difference in strengths. Why, for example, are two of the forces of nature, gravity and electromagnetism, varying with the square of the distance and have infinite range, while the other two forces are confined to the atomic nucleus scales? We don't know that either. So there's a lot of mystery here, and it really revolves around the fact that we don't have theories of physics that unify these four forces in a self-consistent way.
Next question is from Jeff Wolf. Since they propagate in the structure of space-time rather than traveling through space, what is the speed of gravitational waves? Is it the speed of light, and what governs their speed?
In the theory of general relativity, they do indeed propagate at the speed of light. So in the general relativity theory, a gravitational wave is a disturbance created when the gravitational situation changes. So that could be the collapse of an object. It could just be a perturbation. It just could be a rearrangement of material in an object, or an asymmetric supernova explosion, obviously the collapse to form black holes and neutron stars. And in the theory, the signal of gravitational change is a gravitational wave, and the propagation speed is the speed of light. That's what the theory says. We don't have an independent test of that, because it's actually very hard to prove that gravitational waves travel at a particular speed. We have no way to generate them, for instance, in the lab, so there's no version of no hope really actually of a lab experiment to show this. So it's a prediction of the theory, and we've seen nothing that's inconsistent with it so far.
The next question is from one of our live viewers who would like to know, have you had a chance yet to read Dr. Avi Loebs' book, Extraterrestrial? And what do you think his argument is credible for the extraterrestrial origin of Oumuamua?
I haven't read his book. It's on one of my reading lists and a pile of books. I have 3 piles of books that I'm working my way through. I look forward to it, though. He's a very smart guy, well known in my field as the head of, for many years, of the astronomy department at Harvard, and a really good theorist in his own right on cosmology issues. He did vary out of his expertise to deal with Oumuamua, and the consensus of most researchers is that this is a natural object and not an alien artifact. His argument is primarily based on the unusual orbital properties plus the unusual size and shape of it. Now, the unusual orbital properties do potentially indicate that it has an extraterrestrial or beyond the solar system origin. The shape, however, has been refined since he wrote his book or his first article, and it's now no longer quite as extreme, we think, as he was speculating. Also, astronomers have come up with more or less plausible explanations of how it need not be an artificial object in terms of its orbital properties and speed. Researchers at Arizona State University, just up the road from me, released a paper in the last month that makes a pretty convincing case that it's a natural object and not an alien artifact. So I'd say consensus is sort of moving against his idea, but he wrote a book about it. The book's getting a lot of traction, a lot of press. He's getting a lot of interviews. Everyone likes a maverick, especially one that's well-spoken and appealing in his way. So I think that idea will stick around for a while, but it's an unlikely premise.
The next question is related to the recent exciting flight of a helicopter on Mars, and they would like to know why was a drone only sent to Mars so recently, and what challenges stopped them from doing so before?
So I'll sort of treat this as two questions. Let me just talk about the event, the recent event itself, and then I'll talk about the larger context. So yesterday, very recently, an incredible success, a milestone really in our exploration of space, the first powered flight on another planet ever. And if you think about it, Kitty Hawk, first flight of the Wright brothers, 1903, that was the first powered flight on the Earth. So not much more than a century later, we have a powered flight on another world. That's very striking. There's a little connection between the two as well. First of all, it was a short flight. I think the first successful flight by the Wright brothers was 12 seconds. The Ingenuity helicopter on Mars flew for just over 30 seconds, so also a short flight. And it actually had on the helicopter, was a tiny little swatch, a patch of the sail from one of the Kitty Hawk flyers. So there's a little relic of the first flight on Earth on the Mars helicopter. So it's a spectacular success, and that was the event that we've just been hearing about. To the larger issue of why do we do powered flight on another planet, or why has it taken so long to have this happen for the first time, the reason for doing it are pretty clear. Rovers, however well built, can only go a certain distance. Even those very long-lived Spirit and Opportunity rovers eventually were wearing out. They were wearing out their bearings, wearing out their diamond drill bits, and so there's just a longevity limit for these rovers, and they're moving very slowly, so there's just a limit to what ground they can cover. In principle, if you had solar-powered drone or helicopter technology, you could travel large distances, huge distances across a moon or a planet, and that gives you an enormous amount of range. And again, with solar power to replenish the batteries, you could maybe do this for years, many, many flights. So it's very attractive for that reason. It gives you a lot of scope in your exploration. And you get an aerial view and then an up-close view because you have cameras, and so you can settle on an interesting formation and look at it up close. As for why it took this long, it's an extremely challenging thing to do in several ways. The first challenge is just an aerodynamic challenge. Remember, the Martian atmosphere is thin. It's 1% of Earth's atmosphere. So these rotors are not pushing on anything at all like our air. And so it's very hard to test such an object. Of course, it was tested on Earth at JPL, and they used a semi-evacuated situation to try and operate it, and they had to use clever methods to try and simulate 40% of Earth's gravity as well. But it's very hard to do a full heads-up test of a helicopter that's designed for an alien world. That's one problem. So you can only simulate it with computers all you want, but in the end you're going to want to do a real test with a real device. And that means that's been very difficult, and that's taken a long time. The second practical issue is just the difficulty of logistics, because you have a situation where the signal time, depending on where Mars and the Earth are in their orbit, it could take 20 minutes to send a signal to the helicopter to do something, and then it takes another 20 minutes to get the picture back. So if you had a problem or a hazard, it's too late. If you run into something, you wouldn't learn in time to send a command. So basically the robots in these situations have to be autonomous. They have to be able to make their own decisions based on the information they have to hand, because there's no way you can have real-time control over something that's so far away.
The next question is from an email, and John Cody asks, do you think it would be better to drop in unannounced on the home planet of a super intelligent species, something that was less intelligent than us, or a planet that had no intelligence?
Well, it would be nice if we got the choice. I think dropping in on a super intelligent species or set of creatures would be interesting, but lead to very unpredictable results because we simply don't know how they would react. I mean, clearly they would have capabilities beyond anything we present to them, and so in a sense we're unlikely to be a threat. There's also unlikely that we have anything to teach them if they're more advanced than we are. So hopefully that's a pretty benign situation. If we drop in on a civilization that's less advanced than we are, then I suspect our technology will look like magic to them. Arthur C. Clarke had that famous quote, any sufficiently advanced intelligence is like magic. And so our technology will look like magic to these, just as if you flew drones or jet aircraft back at the time of the ancient Egyptians, they'd have no way to make sense of that technology. So that would be interesting too. We could learn about another set of creatures in a situation of control, because we'd have authoritative technology compared to theirs. And then visiting a planet where there's no intelligent life is the most likely scenario, because almost every astrobiologist thinks there are many more worlds out there that have some form of biology on them, where it's mostly primitive or microbial, for every one that might have advanced to intelligence. So in a sense, that's the most likely scenario.
The next question is from Tristan, who would like to know, why is the James Webb telescope going so far away rather than staying in Earth orbit?
That's a good question, because the degree of difficulty and the danger of a Lagrange point orbit very far from the Earth is substantial. The fundamental danger is that the telescope is irreparable. If something goes wrong with it, you can't fix it. There's no way you can send astronauts out there, as we did 5 times on the space shuttle, to fix the Hubble Space Telescope and upgrade it. So that's a fundamental issue. And so clearly you'd have to have a very strong reason to put it so far away from the Earth. There is, however, a very strong reason, which is that low Earth orbit, where the Hubble Space Telescope is not a very good environment for astronomy. It's a great facility, but there's a lot of debris up there, of course. There's a lot of sky glow. It's not glow from the atmosphere, because you're above essentially all the atmosphere, but the atmosphere below you and nearly all around you is glowing. There's earth shine, there's sunshine. You have to navigate all these contaminating sources, and they lead to backgrounds. Then these backgrounds limit your observations. When you get to where the James Webb is going, your situation is absolute darkness. If you have a sun shield, which is the fundamental thing you need to do to stop any sunlight getting on your telescope or your instrument, then the rest of space, everything you're looking at, is completely dark and completely clean and free of debris. So it's a pristine environment. It's the best possible environment for doing astronomy, and it's also very stable.
The next question is, again, related to the Ingenuity helicopter. Can you talk about what the purpose of the Ingenuity helicopter really is on Mars? I was reading that it doesn't have any data collection instruments, so what is the purpose?
The purpose of Ingenuity really is it's a technology demonstration. So it was not built with a autonomous scientific mission or purpose, in part because doing this for the first time and fitting it, of course, into a package that was really similar to what we'd already sent before. Remember that the Curiosity rover is a twin of the rover that went 10 years ago to Mars. And so you didn't have any extra space to squeeze something like a helicopter, so they did some very good packaging to get it in there at all. It's a very small device. It's smaller than many drones actually on the Earth. So it's as small as it had to be to get onto the manifest. It's light, and so it doesn't have scientific capabilities. It has its own camera, a miniature camera, but that's about all. And so it's really just to show that we can do it. And it's, of course, gearing up for a future time when Mars exploration will continue. We'll be gathering samples to bring back to the Earth. We'll be doing reconnaissance for the situation of a Mars base. And of course, helicopters and drones would be a great way to do surveying of a potential habitat where we might build a base. So we have to think long term about why you want to use these technologies on Mars. And I think there are plenty of reasons for it.
Wendy Travers sent an email asking, if it takes an impact or disturbance to set a comet hurtling towards the inner solar system, how do you account for periodic comets?
It's not necessary to have a disturbance to send a comet into the inner solar system. So disturbances, massive disturbances or influences of a giant planet like Jupiter do in fact trigger comets in the Oort cloud to come into the inner solar system. But a lot of comets just have orbits that bring them that way anyway. Remember, the Oort cloud is a repository of comets that extends out to 50 or 100,000 astronomical units, and perhaps 1 trillion objects of a few kilometers in size. That's the totality of the comet cloud. That comet cloud mostly consists of objects that are on extremely elliptical orbits that don't even bring them into the inner solar system, because remember, they're starting thousands of times further out than the outermost planet, so their orbits just don't even span the normal solar system. It's actually a small subset of those comets that have trajectories, natural elliptical trajectories that bring them into the inner solar system, and then an even smaller number whose orbits that may have started in the Oort cloud are perturbed by planets and objects that come nearby to be in an entirely inner solar system or within the solar system orbit. And those are the short period comets. Things like Halley's Comet would be an example. Most of the famous ones, Comet Encke and so on. So we're talking about a tiny fraction of the total comet population that do this. And many of them are caused by perturbations, but some of them just have natural orbits that way.
One of our live participants would like to know, are there any other organisms like tardigrades? Now, I'm not sure what they mean exactly by like tardigrades, whether it's multicellular or whether they mean can survive for long periods. But perhaps you can generally talk about other organisms that might have some similar qualities in terms of astrobiology research.
Right. So the question really is, are there any other extremophiles that are animals as opposed to microbes? So most extremophiles are microbial, and they can tolerate extremes of all manner of physical conditions, of temperature, of density, of acidity, of salt content, and so on. Tardigrades are very unusual. There are no animal extremophiles, if you like, that rival the tardigrade in any way. Now you might just look at members of the animal kingdom, things that are familiar to us from nature shows and David Attenborough and so on, and there are some animals that can tolerate pretty extreme conditions. There are animals that can tolerate lack of water. I mean, camels, for example, can go for a year without a drink. So that's a human being is in very bad shape after a day, deathly ill after 3 days, and dead within a week without water. So it depends what you mean by extremophile. So there are some creatures on the Earth who've learned how to live and thrive essentially in very difficult environments. And if you could call them extremophiles, I suppose, they're not technically extremophiles, but they have some of those attributes. But generally, in terms of its ability to handle enormously less water than almost any other living creatures can, tardigrades are really quite unique.
Irem, who's on with us live, would like to know, is there any work going on to clean up all of the debris from previous accidents in Earth's orbit?
I wish it were the case, but no. There's a lot of discussion about it. So the issue of space debris, space junk, is now top of mind for everyone in the space program, NASA, and internationally, because all countries suffer from this and all have contributed to it. So I guess the best you can say is that it has everyone's attention. Everyone knows it's a problem. Everyone knows it's only going to get worse as companies like SpaceX put up tens of thousands of satellites and the space activity heats up with the private sector. It's only going to get worse, and there's no regulatory authority, the UN or any other body are not able to say you need to fix it and here's how you should do it. So no one's in charge is another issue. And the third issue is technology. What is the technology that would allow you to sweep low Earth orbit of the debris that's already there? So you can try and stop new debris from getting up there, and people are doing that. They're trying to have satellites launched now, especially big ones that naturally deorbit, so they don't sit there as dead hulks that could eventually smash into small pieces. That's a new thing. But the issue of getting rid of what's already there is much more difficult, because once it's gone into small pieces and spread out over this huge surface area or volume in low Earth orbit, we don't have a standard technology to deal with that. People have thought of electromagnetic sweeps, of magnets, of light blasters to sort of move them into lower orbits when they deorbit and burn up, all sorts of methods. Proof of concept is not there yet for any of those methods. They're going to be expensive to play out in large scale. And so I would say, people are just starting to get to serious grips with this problem and what the solutions might be.
One possible, as you pointed out, a way to keep them from becoming space junk seems to be moving forward from Northrop Grumman. There was a recent satellite capture mission that will be boosting a satellite or extending the life of those. Do you think that will become a regular occurrence, and maybe future satellites will be built to be, to have that kind of connectivity for future missions?
I think that for future satellites, and even to refurbish or extend the life or deorbit current satellites, building a capability where with fairly modest cost you can go up and have a probe that will attach to a satellite that has some retro rocket capability and could either boost it into a higher orbit or maintain its lifetime or extend its lifetime, or send it into a lower orbit which would naturally deorbit by drag and burning up in the atmosphere. So I think people are advancing plans for both of those things that would help with the large existing satellite population and build it in to the new satellites that you launch.
The next question is from Joanne Kearney. Is inflation the only theory to explain the homogeneity and flatness of space, or are there alternatives?
Inflation is the best theory to explain them, and that's what it was invented for. Otherwise, you're sort of left with a coincidence. You're left with no natural explanation for it. And the reason why it's an issue is because the Big Bang is a singular event. That's the emergence of all matter and energy from an iota of space-time that's smaller than a subatomic particle at the beginning. And so that's a situation of extreme space curvature as well. Since mass and energy curve space and time, the Big Bang was a situation where space-time was completely knotted and highly, highly curved. So you have to have some mechanism to explain why space-time doesn't even show any curvature now, 14 billion years later. Also, you have to explain why things are so homogeneous, because the early expansion rate of the universe had objects moving apart or mass moving away from other mass at faster than light speed, substantially faster than light speed. And so there's no way in a thermodynamic sense that the universe could equilibrate its temperature from one part of it to the other as it expanded. And so you need a mechanism, you need an understanding of why the temperature of the universe is so different, is so similar in every direction, as we see with the microwave background. So you're either left with positing a very unusual special conditions at the beginning, which is very arbitrary and people don't like that, or you have this inflationary mechanism which does naturally explain those two things.
The next question may take a little bit of interpretation, but we'll give it a try and see if we can figure it out. Makloof asks, why are spiral galaxies considered as standard rulers and calcium emission lines that are very abundant useful for measuring Doppler effects, the Doppler shift in galaxies?
So the issue of what are called standard rulers in cosmology, that's an important issue. When people want to do cosmology, measure the size, shape, and history of the universe, you have to use sort of standard measures because you're dealing with places that are remote and therefore looking back in time. So ideally you want two kind of standards. You want standard light bulbs and standard rulers. You want things that have a well-known physical size so that when you observe their angular size and you know their distance, you can interpret it in terms of the properties of the universe. And similarly with brightness. If you have things that have a standard absolute brightness, then you can use their apparent brightness to say how far away they are and talk about the universe itself. The standard ruler idea for spiral galaxies is tricky because spiral galaxies are not really one shape and size. There are different types of spirals, different winding of the arms, different mass in their bulge and their disk and their halo. And so people have tried to find subsets of spiral galaxies where they do seem to have a standard size. The other problem, of course, is galaxies don't have sharp edges, so they're nothing like a ruler because the stars just fade away into intergalactic space. And so the edge you see just corresponds to the limit of the galaxy where the brightness of stars goes below the sky brightness, and you can't detect them or their contrast. So the idea of standard rulers in cosmology has a very vexing history because it's been very hard to find standard rulers. The other reason standard rulers don't tend to work in cosmology is because the medium between galaxies is not nothing. It's a high temperature, low density plasma called the intergalactic medium. And the interaction of a galaxy with that plasma, with the intergalactic medium, affects its properties, its shape and its size. And so you can't really talk about any standard ruler without understanding the properties of the intergalactic medium. And that's something that we've had a lot of trouble studying in the last few decades.
The next question is from Ahad, who would like to know, does the Astronomy Society, I assume he means the astronomy profession, ever worry about cuts or cutting space research funding?
Yeah, astronomy in its various modes, the national astronomers in the U.S. and astronomy organizations worldwide. So professional astronomers do worry about the funding for their field. There are really two types of funding, though. There's type of funding for research that happens within a country that comes from their funding bodies funded by the government and the taxpayer. So that would be like NASA and the National Science Foundation in the United States. In the EU, it's the EU Horizon Fund and other infrastructure funds and so on. So there's these funding sources, and these funding sources depend on the economy. So the funding for astronomy has done reasonably well. It's not done particularly well, and it's not done particularly badly. It tends to be stable in real terms from year to year. So that's one source of funding. And then the other source of funding is a lot of increasingly private partnerships and consortia that are building some of the world's biggest telescopes. At some level, they're slightly immune from the economic cycle and from government funding because they use foundations, they use endowments of universities, and they do often have partnerships with governments too to get some of their funding. And that funding has actually increased in the last few decades because many of the current huge generation of telescopes under construction are funded by private consortia with some public money, but mostly private. So in that sense, the astronomy funding is quite robust and quite healthy at the moment.
All right, it is 2 o'clock. We have time for one final question for today, and we will be taking that from Gerard, who asks, is the human organism resistant enough for long-term space missions?
The human physiology is challenged by the space environment. So the work that's been done with astronauts in the space station a number of whom have spent more than a year there, shows that they suffer long-term effects. And it's not just the obvious things like atrophying of the muscles and increased brittleness in the bones. It's more profound physiological changes because the vascular system, which is based on capillary action and so on, is profoundly affected by zero gravity. These studies suggest that very long-term exposure to zero gravity will have serious health consequences. So people are fairly sure that if humans spend a long time in space or beyond Earth, they're going to need some sort of gravity environment. Now that will be addressed because I think Mars gravity, although weaker than the Earth, is probably significant enough to avoid most of these issues. But for very long space flights through vacuum and zero gravity, I think the health consequences are quite serious. And nobody's found a easy answer to that, actually, because the research is still undergoing. That was a good question to end with. We had a good variety this week. We'll be back with you again in the future. Thanks for participating. Thanks to Matthew for helping the session along, and Alexander behind the scenes as always.
Excellent. Thank you, everyone. We hope that you have a good rest of your week, and make sure you head over to Twitch this week and check out our live sessions that will be happening there. And so we will not have a live question and answer session with Professor Impey next week, but all of our regular live Twitch streams will continue to happen. So we will see you over there or on the Discord. Take care, everyone.